Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Started up, go.
2, 1, 0, and liftoff, the final liftoff of Atlantis.
On behalf of NASA, I want to thank each of you and your colleagues for all the support you've given us over the years.
It was an emotional end to the Space Shuttle program. Many watched as Atlantis touched down one final time.
Having fired the imagination of a generation, a ship like no other, its place in history secured, the Space Shuttle pulls into port for the last time.
Many also wondered, what now? For decades, we've marveled at these large, majestic space vessels and their capabilities. But bigger is not always better, as technology shows us time and again. Could something this tiny represent the future of space exploration? It's dramatically smaller than what we're used to, and a lot less expensive to build.
So it will allow space-related research at a small fraction of the cost of the big satellites.
With the space program in transition, this is one of the directions aerospace research is heading.
You think, all right, are we going to be exploring space anymore? That actually is providing opportunities for more unmanned missions and for more organizations such as universities to get involved with space exploration.
And thanks to miniaturized technology, we're now able to do more with less.
There's this great vitality now at NASA in terms of smaller things.
I never thought I'd be doing this kind of stuff in my career.
In this episode of Emerging Science, we'll meet some of the Vermont researchers working to send this tiny satellite to the moon for the first time ever. When it comes to rocket science, Vermont might not be the first place that comes to mind. But look closely, and you'll see it's no longer just the NASAs and Boeings of the world developing the most advanced technology. A number of scientists are working together to blaze a new trail to the moon, much like their predecessors did half a century ago.
It's one small step for man, one giant leap for mankind.
That was a really powerful moment for, I think, everyone of my generation. It was what really motivated us to go into this field.
Everything was happening and there was enormous excitement and enormous development because so much had to be done from scratch.
More and more, the science guiding space exploration is coming not just from our urban centers, but from our rural communities and schools, including here in Randolph, Vermont. Its landscape defined by sprawling farmland, Randolph is home to roughly 5,000 people and Vermont Technical College.
We're going to be sending this satellite dish over to one of the bullseyes over on the wall. First one is going to be right over there.
Inside this lab, Carl Brandon students are laying the foundation for Vermont's maiden space voyage.
This is Vermont's first foray into really trying to do a spacecraft. According to our schedule, we'll be the first satellite launched created by any institution in New England. That's pretty neat. We're beating MIT by at least a year.
The challenge? To design and build a satellite capable of traveling around and possibly landing on the moon. Not your typical satellite. A PICO or cube satellite, CubeSat for short.
So this is the basic structure of the CubeSat. It's made of aluminum and it's a 10-centimeter cube, 4 inches, a teeny little thing. CubeSat is a satellite that's developed according to a specification done about 10 years ago so that universities could launch satellites at relatively reasonable cost.
And it opened the door for a modern-day space race among academic institutions. Dozens now are part of a nationwide CubeSat program, working to send their own pint-sized satellites into space. In Vermont, Bill Lakin directs the Space Grant Consortium and NASA EPSCoR programs.
It's a wonderful teaching tool for students. It's also a wonderful tool for developing miniaturized technology.
What are the LED indications?
Working together, 4 Vermont schools hope to make history by sending the first CubeSat ever into lunar orbit.
It's the first project we've done which involves all of our academic affiliates, VTC, Norwich, UVM, and students from St. Michael's.
The project that we're proposing, what we're working towards, would be the first CubeSat to go to the moon, certainly the first under its own propulsion.
We're just in the beginning of this process of being able to take satellites of this size and going beyond Earth orbit.
This is the structure of the satellite, so these boards stack up. There's a connector in here.
Vermont Tech is taking the lead on the Vermont Lunar CubeSat project, responsible for building the satellite itself.
A little computer board in the bottom, and then various other boards depending on what you're doing with your satellite stacked up above. On this end of the satellite, we'll have an antenna that will mount between these 4 legs.
What has become a groundbreaking effort started off as a side project, a curiosity for Brandon.
But I wondered whether it actually could work, so I did some rough calculations and it looked like it could. So then I did a detailed design and we made this rapid prototyping model. So this would be the lunar lander. And then I got a call from Bill Lakin from Vermont Space Grant and said, new grant opportunity just came in.
Carl mentioned to me that he had an idea that you could put a CubeSat on the moon. Now, this was kind of revolutionary because a CubeSat is a tiny little thing. It's 10 centimeters cubed, not a lot of room. And conventional wisdom has always been that there was not enough space in there for propellant to do interplanetary missions. It was thought to be impossible, and Carl thought it could be done.
But when I first got the lunar grant, it really did something, and every time I'd be outside and see the moon, I'd just stare at the moon. It was just a whole different moon now, to think that something that I put together in my hands might be orbiting the moon at some point is just, an incredible thing to think about.
The thought impressed him and his young son Jack.
I can still see the house.
You can still see the house?
Who shares his father's interest in science and affinity for tinkering.
I don't know as much as my dad does.
Well, this is the same size as a real CubeSat, except a real CubeSat would be made of aluminum.
For a 7-year-old, he has a pretty good understanding of CubeSats.
You know why they're sent out? To take pictures of space. That's what space is all about.
So basically, since Jack was born is when I've been working on this. So this is the radio.
Starting the CubeSat project, one of Brandon's first orders of business was getting the right equipment.
And I'm going to clip on that, and so now we've got the 1U CubeSat EPS.
Turned out, many of the CubeSat parts were commercial, off-the-shelf components available online.
These are the containers we get these parts shipped in. This is from Clyde Space in Scotland. So this is another PC-104 board, and these are the batteries, the newer batteries. The antenna we're getting from the Netherlands.
Brandon's team also is developing the GPS board for the navigation system.
This is the GPS receiver. It basically receives signals from 4 GPS satellites up in space.
And is building the ground station, which will communicate with the CubeSat while in orbit.
It'll be orbiting the Earth, and this satellite is going to be moving like this to try and keep up with it. So we've got some of the gears down here that are telling you what the position is. We've got gears up there telling you what the elevation position is. If it can move reliably and if it can track the whole thing reliably within this degree of precision, then we can receive data back from the CubeSat on this dish.
Surprisingly, the largest component didn't come by FedEx. It was plucked right off of Carl Brandon's lawn.
So the satellite dish was up here across the field, right at the edge of the trees. The students came down with a pickup truck and they took the dish apart and took all the parts up to Vermont Tech.
So we took all of that and put it up on the system.
Electromechanical engineering students Wilson Schreiber and Jordan Lyford are fine-tuning the structure they designed, knowing they'll have to impress more than just their teachers to make the grade.
I hope that NASA's going to be pleased with this, and it's
get our foot in the door.
Yeah, exactly. It is really exciting.
They will be out of school by the time this CubeSat heads into space, but they'll be watching, perhaps as professionals in the field.
I did get a phone call from NASA asking me if I'd be interested in some of the work later on, and I am interested in it.
Not everyone gets to work on a space thing, even in college, so I feel pretty good about that.
The Norwich University team can relate.
It's a little claim to fame. Like, hey, I worked on that project, way back in college.
The frame itself is kind of wobbling.
These platforms are pretty stiff.
Mechanical engineering students Matt Wagner and Robert Martin are helping to design the CubeSat's navigation camera under the guidance of Associate Professor Danner Friend.
The aspect of the project that Norwich is working on has to do with taking a camera and capturing images of celestial bodies such as the moon, the sun, the stars, to gather information that would allow the satellite to determine its own position in space.
This is our mock-up CubeSat with a camera in it.
The camera takes a picture, and then that gets transferred onto a board chipset on the CubeSat. And then we do some filtering, and it turns it into like a binary image. It gives us results on like the distance between these two, the distance from the center of the image to the center of the moon, and it's pretty much what we use to calculate where we are in space. This is like the last line of defense for making sure we're in the right spot.
Their goal is to give the CubeSat autonomy, the ability to steer itself, eliminating the need for an Earth-based global positioning system, or GPS.
And this is important for it to be able to keep track of where its position is in space. If it goes off of its intended orbit, we'll have thrusters that will be able to correct its position and bring it back into orbit.
Complete autonomy is unusual, Friend says, but it's the direction satellite travel is headed.
The unmanned missions are leaning more and more toward autonomous capabilities. We've always preceded manned flights with unmanned flights, and in the past that's really been restricted to NASA and large organizations with lots of resources.
The development of the CubeSats has brought, although it's not cheap, it's brought the cost down to what with grant support one can do in a place like this.
An hour's drive northwest, another team of researchers at the University of Vermont is charting the CubeSat's course to the moon.
I'm leading a team to design the low energy trajectory so that we can transfer from lower Earth orbit to lunar orbit.
So we used our three-body model, which included the Earth, the moon, and our spacecraft.
Under the guidance of Jun Yu, UVM and St. Michael's College students are devising mathematical models to test different linear and nonlinear flight paths.
CubeSat is a small satellite, so the restriction on the space, so we only have a limited few.
If we can just perform a maneuver that can get us onto these manifolds, we can save a lot of energy.
Conserving energy on a mission like this is key, which is why scientists are looking to tap the Earth and Moon and their gravitational pull for help.
So as you get closer to the moon actually assists, and it can actually pull things away from the Earth.
Regular straight way that Apollo went to the moon takes a lot of energy in a relatively big rocket, and there's some very unusual flight paths that use less energy.
If we go with the direct transfer, it'll only take a few days, but it will have higher energy expenses. If we study the nonlinear dynamic of the system, we choose the lower energy trajectory, it will take less energy, but it will take longer.
When we go to the moon, we'll get a launch to a geostationary transfer ellipse, and then we'll gradually enlarge the ellipse with the ion engine until that ellipse reaches about 3/4 of the way to the moon, and then you flip into an ellipse around the moon and gradually make that smaller until you get into a final orbit around the moon. That takes about 14 months to do that. In addition, the flight paths that we're looking at would go through the Van Allen radiation belt a number of times and expose the spacecraft to a lot of radiation, so they're modeling that to see how much radiation, and we have to figure out what we have to do to mitigate problems from radiation with the equipment.
Problem solving like that is the main focus of mechanical engineering professor Doug Fletcher, though he is not involved in the CubeSat project itself.
Power on.
He runs a plasma diagnostics and torch facility in the basement of this building at UVM. to stress test aerospace materials that cover and protect spacecraft traveling through extreme conditions.
So the materials have to withstand significant heat fluxes that are generated as the vehicle flies through an atmosphere at very high speed.
Walt's going to start the facility with argon, and that's the easier gas to couple to create the electron population we need. And then from that point, then we go up in power and we go up in pressure to get to the design pressure that we want to run at, and then we transition over to the test gas we want to run.
Ready, Walt? You ready?
Yep.
All right, power on.
Students and researchers run material samples
This material is graphite
through a machine that mimics conditions created by high speeds, soaring temperatures, and a variety of atmospheric gases.
This is the same material after it has been tested.
Conditions a spacecraft could encounter on a mission.
So we can create the gas mixture that represents the planetary atmosphere, and we can run the test, and we can even tell people whether their material performs better in one atmosphere or another atmosphere. As far as I know, we are the only inductively coupled plasma facility operating in the US at present that's designed to test thermal protection materials.
The work Fletcher is doing is breaking new ground, much like the Lunar CubeSat project, and has great short and long-term potential. The immediate goal here is to successfully reach lunar orbit. Landing a miniature spacecraft on the moon is a more distant proposition.
The landing one, I think, is probably less likely to happen because of the flammable propellants going on a ride with a several $100 million communication satellite.
Not an impossibility, just a longer-term project. With the same kind of time frame Jeff Frolic, another UVM scientist, is anticipating.
Our work is decades away from implementation. You have to start somewhere.
Frolic is involved in the remaining piece of Vermont's CubeSat research, communication and data collection via wireless sensors.
Okay, yeah.
We're looking at what might happen far in the future when we have these CubeSats, and what would happen if we send a whole bunch of them to the moon or to Mars and whatnot. The idea is, how can we even set up the framework for things that are already landed to communicate with things that are still moving.
These are wireless sensor modules.
Graduate student Greg Carpenter is helping Frolic design a system of sensors that will work, at least to start, on a small scale.
So what they do is they take turns. One of the things we're doing to model the behavior of the CubeSat mobile resource and the planetary or lunar sensors is to use this quadrotor helicopter robot. And that's it waking up. What this does is it can fly out to within a close range of sensors like this and communicate with them, collect data, and bring it back.
So we're looking at potentially putting sensors across a field and then having our quadrotor fly around the field and communicate to individual sensors. Once things are on the moon or on Mars or whatever, obviously the scales are much bigger.
Why this is useful in the context of the CubeSat program is that these CubeSat satellites actually can work in cooperation with sensors that have been deployed down on the surface of Mars, the moon, whatever, and actually collect data from them. So these things will communicate messages to this, and then this will bring the data, or in the case of the CubeSats will then act as a secondary communication point to bring the data back.
Although it will be years before a system of sensors like this is ready for use in space, Frolic sees many more immediate uses here on Earth.
There are a lot of environmental applications that are remote, and you would like to be able to get data from, let's say, a forest or ice pack.
Getting the sensors to work relies on communication and cooperation, two key elements of the CubeSat project as a whole. Each research team must do its part to ensure the mission's success.
We're all kind of working on different aspects right now, and for something like this to actually be pulled off on a grand scale, it is going to need a whole bunch of different components.
One of the key goals of Vermont Space Grant Consortium and Vermont NASA EPSCoR is to develop the research infrastructure in Vermont
Among the students and faculty involved in Vermont's Voyage into space is a shared sense of excitement and opportunity. For many, this type of work is an unexpected first.
And I actually was never involved in this kind of research, in space research, and then all of a sudden I have a whole new career, you know, starting at age 60. So.
Ever since I was little, I've always wanted to learn more about space, and there's so many different opportunities for discovering possibly life on other solar systems.
Developing CubeSats is a perfect fit for academia. No massive budgets or trained astronauts needed. And the final product, a spacecraft small enough to sit in the palm of your hand.
Most spacecraft are very large. They cost a large amount of money to be able to launch them.
CubeSat I could get going with $195,000. Space Shuttle, $195 million would not be enough.
I think the idea behind CubeSat is that they are very low cost, almost disposable if you think about them that way.
The advantage of a miniature satellite is that it can hitch a ride aboard a rocket.
Right now, anytime there's a commercial launch, there's always ability to carry more weight. And they're putting a number of CubeSat launchers on these rockets, and you get a piggyback ride. So after they deploy the main paying satellite, the CubeSats get popped out from these launch boxes.
It will be launched in what's called a P-pod, which is a special launch apparatus that was designed out at Cal Poly. And that makes it very, very safe to launch.
You could launch 20 of these, and if a few of them or half of them fail, you still have many that could succeed, again, at the fraction of the cost.
And with the tightening budgets for NASA, it allows things to be done that couldn't be done within the budgetary limitations and with larger spacecraft.
While the field of space exploration has grown over the years, the very technology used to build these complex spacecraft has shrunk.
If one's talking about 20 years ago, then you couldn't do the kinds of things that they're doing now. This CubeSat mission would be impossible.
People are developing very sophisticated instruments for CubeSats, because of the miniaturization that's possible today.
Some of the benefits of this type of research is that we can take existing technologies that are currently being used, things like smartphones, that are miniature electronics, apply that current technology to a different application, a spacecraft, that we can now show that these available components at a relatively low cost can be used to actually do sophisticated space exploration.
I want to see a rocket launch. I wanted to see a rocket launch since I was a kid, so.
Carl Brandon may soon get his wish. The Falcon 9 rocket, developed by a private company, SpaceX, is being tested as a replacement for the Space Shuttle. Its mission? To resupply the International Space Station. And if the Falcon 9 launches as scheduled in March of 2012, Vermont's CubeSat will be in tow.
That's going to be pretty exciting.
It will be the first hardware completely made in Vermont will be into the space.
The 2012 launch will send this single CubeSat into orbit roughly 200 miles above the Earth, with the objective of testing the satellite's navigation system. If all goes well, work will begin on Vermont's next spacecraft, a triple CubeSat to orbit the Moon, an unusual mission for a satellite of any size.
Having a successful launch and testing the navigation system, we would apply for the sort of next size NASA grant. I actually got a 50-page document from NASA on all the things they want to learn about the Moon that they haven't done yet.
This lunar triple could take 5 or 6 years for Vermont scientists to develop. But they say after that, the possibilities are endless.
The Moon provides really just the first step to go beyond our own area around the Earth. So going from the Earth to the Moon would be a huge step in advancing the ability to go further. So maybe the next step would be to go to Mars.
Vermont researchers are helping to pioneer a new chapter in space exploration, providing valuable information to the scientific community and securing a new regional presence in the future of aerospace research.
It's very exciting because for this small CubeSat, nobody has done this yet. So Vermont will be leading in this area.
Vermont, of course, being relatively remote from any NASA center, didn't have much connection with NASA in the early 90s. Now, with computers and link-ups and broadband, one can access NASA data sets, which most of our projects do, and one can basically work from anywhere.
Being a part of that process to explore new areas in our solar system, that will eventually hopefully lead to being able to determine whether there's maybe life out there that we don't know about.
For Carl Brandon, it would be a professional and personal achievement. Brandon takes pride in knowing that CubeSats have opened a new door for the next generation of scientists, allowing them to build on their dreams for exploration.
There's a possibility that in 6 years or so, we may have a CubeSat a foot long orbiting the moon that I built with my hands.